Usually when we hear the words container orchestration, the image that immediately flashes into our minds is just massive and incredibly complex.
Oh, absolutely.
Like you picture something like Kubernetes, right? You imagine this entire engineering team sitting in some heavily air-conditioned control room.
Right. With monitors everywhere.
Exactly.
Yeah.
Monitoring a computing cluster the size of a small city just to keep a web application running without crashing.
Yeah, it definitely has that really intimidating reputation.
It feels like this exclusive domain where you need, an advanced degree in distributed systems just to get a simple server off the ground.
I mean, the industry standard right now heavily leans toward those massive, highly abstracted systems,
Hmm.
which, they're fantastic if you're running a global streaming service,
Sure.
but they're completely overwhelming if you are just a solo developer or like a small organization.
And that is exactly why today's stack of sources is so refreshing. We are exploring this really fascinating middle ground.
Yeah, it's a great stack today.
So for this deep dive, we're looking at research papers and technical notes by Dashmir Hoxha, and these detail how to run entire Linux desktops and WordPress sites inside containers.
Right.
Plus, we've got a comprehensive architectural breakdown of the Docker scripts ecosystem. And to cap it all off, we're pulling from the official GitLab CI/CD pipeline configuration reference just to see how all this stuff actually gets tested.
It is a phenomenal combination of materials, honestly.
Yeah.
What emerges from these sources is this very empowering idea. This idea that enterprise-grade IT infrastructure,
Yeah.
secure, isolated, scalable, it doesn't have to be totally out of reach just because you don't have a dedicated IT department.
Right, and that's our mission today for you listening. We want to demystify this. We want to show you how secure web hosting, multi-tenant databases, even entire virtual computer labs can be managed by a single person.
Exactly.
Okay, let's unpack this. Because to understand how you can run a web agency or a school's computer lab from just one server, we have to look at the engine powering it.
The core of it.
Right. The sources refer to the DEDS utility or Docker scripts. Now, looking at this, it's not some giant software suite. So how does this actually work?
So think of it as a meta orchestrator,
Mm-hmm.
but one that basically strips away all the heavy abstraction.
Okay.
What's fascinating here is instead of hiding the container runtime behind a really complex API like Kubernetes does, Docker scripts is a framework built entirely on technologies that system administrators already know and trust,
Like what?
like Bash scripting, M4 macro expansion, and the Docker engine itself.
Oh, wow, just standard tools.
Yeah, standard tools.
Mm.
It creates this highly structured, predictable lifecycle for applications without requiring you to learn a completely new orchestration language from scratch.
I'm looking at this life cycle in the architecture doc, and it seems remarkably straightforward compared to, writing massive YAML files.
Oh, it's night and day.
I really want to understand the mechanics here. How does an app actually go from just a repository to a running container?
So it happens through four distinct, very mechanical phases. It starts with acquisition. You just run a command, dz pull.
Okay.
Mechanically, what that does is it reaches out to a specific GitLab repository and pulls down the specialized scripts and Docker files for whatever app you want, say WordPress or maybe a database.
Right, so you have the ingredients.
Exactly.
Okay.
Then comes initialization using the command dzrun.
It.
Yeah.
Yeah.
This creates a completely isolated directory on your server for your specific instance of that application.
And that brings us to the configuration phase, because the sources put a massive emphasis on this single file called settings.esh.
Yes.
And if you're listening and thinking, I don't know the first thing about bash scripting, is this really for me? I think this file is the answer.
It really is. That file is the core of the framework's simplicity.
How so?
Well, when you initialize that container directory, the system automatically populates settings.esh with default values. As the administrator, you don't actually have to write code.
You just edit?
Right. You just open that text file, uncomment the variables you need to change, like setting your domain name or maybe establishing an admin password, and you save it. It acts as your single source of truth.
But a text file full of variables isn't a running server.
No, it's not.
How do those variables actually get injected into the complex server configurations? Because the sources mention M4 macro expansion, which honestly sounds like a leftover term from a 1980s spreadsheet. What is that actually doing?
Yeah, it sounds ancient, but it's actually a very mature piece of Unix history.
Yeah.
Think of the M4 macro processor as a heavy-duty, highly dynamic find and replace engine.
Okay.
And that brings us to the final phase, instantiation, which you trigger by running deeds make.
So what happens when you run that?
When you run in deeds make, M4 basically wakes up, It reads your settings.h file, takes all those variables you just set, and dynamically injects them into the raw configuration templates right before the code executes.
Oh, wow.
Yeah, it generates the final, really complex Docker commands and service configurations on the fly.
So it sounds like a meal kit delivery service for servers.
That's a good way to put it.
Like, instead of going to the grocery store, hunting down all the individual raw ingredients, and trying to guess the ratios for a recipe, the Deez utility just gives you the pre-measured ingredients, right, the scripts, and a standard recipe card.
Yeah, exactly.
You just tweak the seasoning in that settings.shf file to your liking, and the M4 processor basically cooks the entire meal for you.
That is a highly accurate way to visualize it. You get the consistency of a standardized recipe, but the total flexibility to season it however you need.
Right.
And that flexibility, it extends to how it handles multiple identical applications too. The framework uses a very simple @ symbol in its naming convention.
Like in an email address.
Yeah, exactly.
Yeah.
So for example, you might initialize an app by typing Deez init app at instance 1.
Oh, meaning I could easily spin up like app at staging and app at production right next to each other on the exact same server?
Precisely. The @ symbol basically mechanizes the isolation. It tells the scripts to create distinct directories and unique internal Docker network names for each instance.
That's so smart.
The sources actually refer to this as a poor man's orchestration layer.
I love that.
It gives you a multi-tenant architecture that is human-readable and highly portable, all without the overhead of some massive cluster.
Okay, so we've seen how efficiently this framework builds the containers, but that leads to an obvious mechanical problem.
Right.
If I'm hosting a dozen different WordPress sites for different clients on this single server, they are all trying to use the same front door, basically.
Yeah, they are.
How does a server know where to send a visitor when they type a specific URL into their browser?
That requires a routing mechanism.
Yeah.
And in this ecosystem, the architectural linchpin handling that is a container called Roost Proxy.
Roost Proxy.
Yeah, it functions as a reverse HTTP proxy.
So it's kind of like the mailroom at a massive corporate headquarters. All the letters, no matter who they're for, come to one single street address, your server's IP address.
Right.
But the mailroom opens the outer envelope, reads the attention to line, and slides the letter into the correct internal departmental chute.
That analogy fits perfectly. Mechanically, Drevis Proxy is the only container that is actually exposed to the public internet. It listens on ports 80 and 443.
Okay.
All your individual WordPress containers sit safely behind it on an isolated internal Docker network.
Oh, nice.
So when a web request hits the server, Drevis Proxy reads the HTTP header. Your attention to line looks at the requested domain name and instantly routes that traffic to the correct internal container using Apache Virtual Domains.
Which is brilliant for security because your actual application databases aren't even touching the public web.
Exactly. They are completely hidden.
But what really caught my eye in the Hoxha papers is how this mailroom handles SSL certificates. Because if you have ever pulled your hair out trying to manually generate and renew security certificates for a website, you know it is just a nightmare.
It is traditionally a very brittle process. Things break all the time. But here, Rest Proxy automates modern web security standards by default. It natively integrates with Let's Encrypt.
How seamless is that integration?
Very. When you initialize a new site and declare its domain name, Rest Proxy automatically triggers an ACME challenge.
Okay.
It reaches out to Let's Encrypt, proves it controls the domain, acquires the cryptographic certificate, and configures the HTTPS routing, all without you typing a single extra command.
It just removes a massive manual burden. And speaking of removing manual burdens, if you are a developer, the as site clone command detailed in the WordPress document is going to be your absolute best friend.
Oh, it is a remarkable piece of automation.
Because if I want to clone a live site to make a staging environment, doing that manually means exporting the database, zipping the files, moving them, importing the database,
It takes forever.
and then painstakingly running SQL commands to replace all the live URLs with the staging URLs. But Diz Site Clone does all of that mechanically in one command.
Command.
It backs up the source, initializes the target, restores the data, and automatically performs that database search and replace for the URLs. It basically turns an hour of caffeine-fueled stress into a 10-second wait.
It drastically lowers the barrier to proper testing. However, the sources also point out a critical architectural trade-off that administrators have to wrestle with when hosting multiple sites like this.
Right, the multi-tenant dilemma.
Yes, the classic multi-tenant dilemma. Do you consolidate multiple WordPress sites into a single shared container, or do you give every single site its own isolated container?
See, I have to push back on the idea of consolidating them.
Why is that?
Well, the sources say grouping them saves RAM and disk space. But wait, putting a dozen client sites in one container? If one of those sites gets compromised because a client installed like a bad, outdated plugin,
Yeah, the attacker is inside.
doesn't the attacker now have access to that entire container? Why would anyone risk taking down 12 clients just to save a few gigabytes of RAM?
You're hitting on the exact friction point the sources highlight. You are absolutely right about the risk profile. If they share a container, they share a file system and a PHP execution environment.
Right.
The blast radius of a compromised plugin is the whole container. But you have to view this through the lens of a solo educator or a small NGO operating on a shoestring budget.
Okay, I can see that.
If they only have a $10 a month virtual private server with, say, 2 gigabytes of RAM, spinning up 12 separate MySQL databases and 12 separate PHP processes, one for each isolated container, it will instantly crash that server.
Because it just runs out of memory.
It will completely run out of memory.
Okay. So it's the classic hotel scenario. You can put everyone in a shared dorm room to save money, but if one person catches a cold, everyone gets it.
Yes.
Or you give everyone their own private room. It costs significantly more space and money, but the walls keep the cold from spreading.
Exactly. Putting each site in its own isolated container consumes far more resources, but it provides strict security encapsulation at the kernel level.
That makes sense.
The beauty of Docker scripts isn't that it forces you into one choice, though. It's that it makes both architectures equally easy to deploy, allowing you to choose your acceptable level of risk versus cost.
Okay, so we've seen how efficiently this routes small packets of text and images for websites. But here's where it gets really interesting.
It really does.
The real test of this reverse proxy architecture is whether it can handle a continuous, heavy stream of graphical data. Because the sources reveal they're using this exact same Docker scripts framework to host entire graphical computer desktops.
Yeah, this is perhaps the most ambitious application detailed in the research, the Virtual Computer Lab, or VCL.
I want to make sure I understand the mechanics of this. We are talking about running a full Linux desktop operating system like Ubuntu or Linux Mint inside a Docker container.
Yes.
And then a user accesses that desktop purely through a web browser, no client-side installation, no special software. How does a normal web browser render a full remote desktop?
It utilizes an open source gateway called Apache Guacamole, which runs on port 444.
Oh.
Yeah, Guacamole. Mechanically, it sits between the containerized desktop and the user. The desktop container is running a standard remote desktop protocol, or RDP, which a browser cannot understand natively.
Right, browsers don't speak RDP.
Exactly. So Guacamole intercepts that RDP stream and translates it on the fly into standard web technologies. It basically uses an HTML5 canvas element.
So the server is essentially drawing the desktop as a rapidly updating picture directly into your browser window.
That's the mechanism, yeah. And simultaneously, it captures your keystrokes and mouse clicks in the browser and sends them back through the gateway to the container.
Wow.
So a student doesn't need a powerful laptop. They could be on a decade-old Chromebook or even a tablet. They just need a browser tab. The server in the lab is doing all the heavy computational lifting.
The collaborative features described here are incredible for education, too. Because the desktop is fundamentally just a web stream, if a teacher wants to demonstrate a complex coding environment, they can log in as admin, enter watch mode, and share a link. And suddenly the whole class is watching the teacher's desktop in real time.
And it goes even deeper than that. If a student is stuck on a bug, they can use collaborate mode.
How does that work?
Because Guacamole multiplexes the inputs, multiple people can literally share control of the same mouse cursor and keyboard to debug code together, right in the browser.
That's so cool. And we saw how vital this architecture became during the COVID-19 pandemic. The Hoxa paper details how this framework successfully pivoted into a distributed computer lab.
It was a crucial pivot.
But how did they handle the networking? Because if students are at home, they're behind standard home internet routers, which block incoming connections. How did the students even connect to the lab?
They integrated WireGuard VPN into the ecosystem.
Okay.
WireGuard creates a secure encrypted tunnel that punches right through those complex home network firewalls. Mechanically, it assigns each student's home computer a virtual IP address on the school's internal network.
Oh, so the student's living room laptop behaves exactly as if it were physically plugged into the Ethernet switch in the school's lab.
Precisely. And because they were all tunneled into this secure virtual network, teachers could seamlessly use standard classroom management tools like EPOPs, to monitor all the virtual screens.
Oh, right, because they're on the same local network,
Well,
virtually.
they could provide remote assistance, completely bypassing the limitations of the public internet. If we connect this to the bigger picture, it represents a fundamental shift toward a stateless infrastructure.
Explain that distinction for us, actually, the stateless versus stateful.
Sure. So the heavy, complex graphical environment, the operating system, the installed applications, that is stateless. It is completely disposable. Yeah. If a student accidentally deletes a critical system file and the desktop container crashes, the administrator doesn't spend hours troubleshooting it.
They just nuke it.
Exactly. They just destroy the container, and typed's make to spin up a fresh, perfect copy in 10 seconds.
Wow.
But the user data, the student's actual homework and code, is stateful. That data lives outside the container on the host server, managed and protected by simple commands like these users backup.
This all sounds amazing, but I have to play devil's advocate here.
Go for it.
I am reading this, and we are talking about running entire web agencies, hosting dozens of databases, powering virtual schools, all relying on this one ecosystem. And you said it's fundamentally built on bash scripts and M4 macros.
I did.
Isn't that inherently fragile? Like, isn't this entire system just held together by digital duct tape compared to a self-healing enterprise orchestrator? How does this not just catastrophically fall apart the moment a script has a typo?
This raises an important question, and it's a very valid concern. If you look at the comparative analysis in the sources, they address this head on.
What do they say?
Well, Docker scripts isn't trying to be Kubernetes, right?
Yep.
Kubernetes is engineered to manage thousands of physical servers. Docker scripts is optimized for the single server, many apps reality.
Right.
But to ensure those scripts aren't just fragile duct tape, the project rigorously applies modern DevOps practices. So, what does this all mean? We've covered some serious architectural ground today. We started by looking at how a carefully engineered set of bash scripts and macros can basically replace the sheer nightmare of learning a massive container orchestration language.
We saw the mechanics of how it acts as a mailroom, securely routing traffic with automated SSL certificates. We debated the multi-tenant trade-offs and explored how it translates remote desktop protocols into a web browser to run virtual schools. It takes the sheer power of enterprise architecture and distills it into something a single person can wield.
And it leaves us with a truly provocative thought to mull over, one that actually stretches beyond just software.
What's that?
Well, we've talked extensively about how efficient this system is, how it can run an entire virtual lab or a dozen websites on a single low-resource server. But think about the environmental implications of that.
Oh, interesting. How so?
E-waste. The traditional model of a school computer lab is buying 30 brand new laptops every 4 years because the local operating systems get too bloated.
Right, they just slow down.
But with a framework like Docker scripts, the heavy lifting is moved to one centralized server. Those 30 students could be using decade-old, recycled hardware or cheap, thin clients because all they need is a web browser. If the software abstraction becomes this efficient and this accessible to a solo educator, it completely shatters the e-waste cycle.
That's incredible.
And it also makes you wonder, if the technical barriers drop to basically zero, will the system administrator in the future even need to be a networking expert? Or will they just be educators and creatives, limited only by what they decide to build?
I love that perspective. By mastering the software, we can fundamentally change how we consume the hardware. We started this deep dive talking about how modern container orchestration can feel like trying to manage an intimidating, sprawling metropolis. But what we found here is a beautifully engineered small town.
Yeah.
Everything has its place, the plumbing makes sense, and you don't need a massive army to keep the lights on. Thank you so much for joining us on this deep dive. We hope it inspired you to think about how you might use these tools to simplify and maybe even green your own digital projects. Until next time, keep exploring.